25 years in Korea.
Uh-huh.
So he's almost Korean. Korean Uzbek speaker. So more than 30 years in Korea.
Okay.
The Dongguk University.
Okay, Professor Yudashev, are you ready?
Yes, but sorry, I cannot see. Okay, yes. I cannot see Mr. Michael. Was done in tight collaboration with my Korean friends, Dr. Yoon Intak, Dr. Cho Hak-dong from Dongguk University, and Dr. Kim Jin-sang from KIST. Okay, I'm sorry, I saw my outline. Okay, outline of my presentation is, first of all, I would like to remind you what is the mean conventional Seebeck effect. Okay, then is a new type of Seebeck effect, is the spin Seebeck effect. Then briefly about three-dimensional topological insulator, and our observation of spin Seebeck effect in this smooth telluride is a topological insulator. And then is conclusion. Okay, conventional Seebeck effect was discovered in the 19th century by Thomas Ergan Seebeck, German scientist, in 1821 year. Okay, and the effect is two metals contact under gradient temperature. You can observe appearance of electromotive force. Okay, and this value we use now for thermocouple to measure the temperature. Just by measuring potential, we can determine the temperature. Okay, after that, such kind of effect was discovered in semiconductors, and semiconductors, this effect is several orders higher than in metals. Okay, and here in figure 1 is shown thermoelectric generator made from semiconductors. You can see this consists of two types of semiconductors, N-type and P-type, and electron and holes from hot side going to cold side and accumulated, and after that appears the electromotive force. Okay, thermoelectric materials which capable of direct energy conversion, okay, great significance in energy field. Okay, what are the advantages compared with other source of electron field? Solid-state device without no moving parts, no environmentally harmful fluids, no noise, long operation life, and smaller operational cost. To determine the efficiency of thermoelectric materials, it was used figure of merit. You can see from equation, this is the proportional to square of Seebeck coefficient, proportional to electrical conductivity, but inversely proportional to thermal conductivity. Okay, and then very recently in 2008, the new Seebeck effect, which called spin Seebeck effect, has been observed in ferromagnetic metals like thermowire. Okay. After that, just 1 year, 2 years after that, spin-Zeebeck effect was discovered in ferromagnetic semiconductors like gallium and arsenide, and even in ferromagnetic insulator. Okay, and after that it was supposed effect can be observed in magnetic materials only. Here in figure 2 show the experimental results of spin-Zeebeck effect measurement in ferromagnetic metals. You can see under thermal gradient, the carriers moving from cold side to hot side. Okay, but because it is a ferromagnetic materials, the electrons have spin. Direction is already known, and this electron will spin up. I'm sorry, here the spin is in plane, but usually we use, when we talk about spins, up and down, but okay, in one direction of spins accumulated on both sides, while the electrons with opposite spin accumulated on both sides. And you can see after spin injection in electrode made from very heavy metals like platinum or tungsten, then due to inverse spin Hall effect, there is appeared some electric field on electrodes. You can see, okay, and what is the difference? On hot side, the direction of electric field is one direction, but on cold side is absolutely opposite, okay? And then it was supposed that it should be magnetic materials, because in ferromagnetic materials, spin up and spin down concentration is not equal and determined. Okay, but in 2010, Jaworski from Ohio State University observed the spin-Zeebeck effect in non-magnetic material, indium antimonide. But to observe the spin-Zeebeck effect, he used very huge magnetic field to make spin polarization. Okay, and because the Zeeman effect is very strong in indium antimonide, at low temperature, the main concentration of electron have one spin direction. Okay, after discovery of topological insulator, about topological insulator very briefly is new, okay, not new materials, but new properties. It is usually insulator because this is we can call semiconductors or insulator. In bulk, as usual, electronic structure have a conduction band and valence band, but on surface you have a metallic state, no forbidden gap. Here is no forbidden gap. You can see, okay, no forbidden gap. And what is the most important for us is spin momentum locking of charge on these surfaces. This means spin is perpendicular to momentum, and after that, topological surface of topological insulator determines the direction of spin. This means spin polarization is known, and this may be used for spin generation and spin accumulation. Okay? And such kind idea was tested by us. The samples of bismuth telluride is a topological insulator. Now we understand between the thermoelectric materials, bismuth telluride at room temperature has the highest figure of merit, and this is because, now we understood, this is because it's a topological insulator. Okay, and three types of samples was grown on bismuth telluride on the arsenide substrate. Okay, first we call it L1. This is a bismuth telluride thin film, 200 nanometers thick, was grown on substrate gallium arsenide 001 crystal direction, but it was miscut 4 degree to make epitaxial growth. Okay, epitaxial growth on 001 also, but when it's in miscut, then there is no difference in crystalline structure, and the films grown high quality. Okay, and third one was also made grown on tilted gallium arsenide, but thickness was much higher.
Sorry for disturbing. So, Professor, you will be showing the 5th slide right now. Maybe talking about 6th, right?
Okay.
Yes.
On you can see only
5. Page 5. So maybe this is stopped.
Okay. I saw you see only topological insulator picture. Yes.
Yes. So how about can you share it again? Okay.
Okay. Here is the samples. Okay. As I told you, 3 kinds of samples. 1 to 3 different thickness, and also some difference in substrate direction. Okay, it was on 4 degree tilted gallium arsenide grown with the epitaxial layer of bismuth telluride. Okay, here shows on figure 5a shows the XRD pattern of the film L1 and L2, and you can see the quality of samples grown on this type substrate is the best. Only bismuth telluride with direction 006 is shown, and very small from gallium arsenide substrate, but no other crystal direction was observed. While in film L2, which was grown directly without miscut, you can see there is some crystal domains with different additional crystalline direction. This is clearly seen on figure 5b. You can see the low part L1. You can see this is smooth. No any other maybe other direction, one color. Okay, and this is a image of electron beam backscattering diffraction figures image. Okay, while in sample L2 you can see different colors. This shows that the crystal consists of domain, and this domain is rotated on 60 degrees. Okay, and in figure 5c shows same measured by Namarsky microscope, and on sample L2 we just by this arrow shows the grain boundary between two domains, two crystals rotated on 60 degrees. Okay, on figure 6 shows the electrical transfer parameters of these films, and you can see the first figure 6a. Here is the resistivity, and you can see the resistivity highest in sample L3 Okay, and this is because of lowest concentration between these three samples. The lowest concentration difference at room temperature about 1 molar between L3 and other films. And you can see in figure 6C, mobility on sample L3 is the lowest. Okay. And then here is schematically shown how was measured spin Seebeck effect. Okay, here you can see the sample. Okay, and on hot and cold side is made electrodes, very thin, about 5 nanometers, made from platinum to absorb the spin Seebeck effect. In X direction is the usual Seebeck effect, and the results is shown on figure 7b. You can see the highest Seebeck coefficient observed in L3. Okay, and this was by full lines shown theoretical calculation by using Mott formula, for which he provide for metal and heavily doped semiconductors. And you can see spin, no spins. Seebeck effect value is inverse proportional to concentration. After that, the highest Seebeck coefficient was observed for sample L3. Okay, and now in figure 7C shows the measurement of spin Seebeck effect. This means in y direction. Okay, and you can see here also the highest value of spin Seebeck effect was observed, spin Seebeck coefficient was observed for sample L3. Okay, about 40 microvolts at room temperature was observed. To show this is because of spin Seebeck effect and not some other, we use some sample with same samples was made electrodes with aluminium. Aluminium does not show any inverse pinhole effect. And after that you can see on the samples at same gradient of temperature, spin Seebeck effect was 0. This means is not some on appearance of gradient of temperature in y direction. It's also possible. But this result shows that this is directly connected with spin Seebeck effect. Okay, in conclusions, spin Seebeck effect was observed in the thin films of three-dimensional topological insulator, bismuth telluride, and these semiconductor materials with high value of usual Seebeck effect, and also shows the highest spin Seebeck effect. Okay, spin momentum locked surface state provides the spin polarization of electrons on surface and can be used in the spin current generator. Under temperature gradients, the accumulation of electrons with opposite spin direction on hot and cold side have been observed. And most important, spin Seebeck effect in bismuth telluride topological insulator was measured without using any external magnetic field. Okay, and what I would like also to add. Okay, thank you. So, I'm sorry, very briefly because I spent a long time to make this presentation.
No, it's okay. Thank you to the finishing in time. So, is there any questions or comments?
I think one should use this microphone. The question concerning the spin Seebeck effect, does it mean that it is a bit different than the classical traditional or spinless Seebeck effect, right? In principle. And I mean spin Seebeck effect.
Yes.
Does it mean that if one considers thermoelectricity in these materials, this will be some new kind of thermoelectricity, spin thermoelectricity or something like this? Because Seebeck effect is somehow related to thermoelectricity too, right?
Yes.
I see. So this, and then would that kind of thermoelectricity be better than the classical or traditional one, or something? Are there some advantages of this thermoelectricity compared to the traditional one?
Okay, thank you for your question. It's very interesting and very useful. Okay, first of all, it can be added to usual Seebeck effect. Okay, this means you have additional electromotive force. Okay, this is lower than usual Seebeck effect, but in any case is more than 20%. But most important, not the usual electric motive force, but the spin generator. Because of spintronics, the area of electronics, supposed to inject not just type carriers but spin.
I see. So, then should we say that it is more important from the viewpoint of practical applications in spintronics rather than thermoelectricity?
Yeah, sure.
Thank you very much.
Thank you.